There is a place you can never go, a realm forever sealed behind walls not made of matter, but of mathematics, of time itself. Stand anywhere in the cosmos, look in any direction, and you will eventually hit this barrier. Not a physical edge, not a membrane you could touch, but something far more absolute. A horizon carved into the fabric of reality by the speed of light and the age of the universe. Beyond it lies everything we can never see, never reach, never know, and it is vast beyond all human comprehension. The observable universe stretches 93 billion light-years across. Within this sphere float 2 trillion galaxies, each harboring hundreds of billions of stars. Planets beyond counting, clouds of gas collapsing into new suns, even now, 13.8 billion years after the beginning. This is our cosmic home, our island of light in an ocean of unknown depth. But make no mistake, this island has shores, and we are standing on them, staring into an abyss that stares back with perfect, indifferent silence. What lies beyond? The question feels simple, childlike even, but it cuts to the deepest mysteries of existence. To answer it, we must first understand why there is a beyond at all, why the universe, infinite or not, hides most of itself from us. And the answer begins with the most fundamental law of nature, a speed limit written into the source code of space-time itself. Nothing travels faster than light. You have heard this before. Perhaps it sounds like a rule, arbitrary as a traffic law. But it is not a rule. It is a consequence of how reality is structured at its most basic level. Space and time are not separate things. They are woven together into a single fabric, space-time, where every object traces a path through both dimensions at once. When you sit perfectly still, you are actually moving through time at maximum speed. When you move through space, you trade some of that temporal velocity for spatial velocity. Light moves through space so quickly that it does not move through time at all. Photons do not age. They do not experience duration. From their perspective, emission and absorption are the same instant. This is not a technological limitation. You cannot build a faster engine. You cannot find exotic matter or clever loopholes. The speed of light is the speed of causality itself. It is the rate at which cause and effect can propagate through the universe. If you could exceed it, you could send messages into your own past. You could become your own grandfather. Reality would collapse into paradox. So nature forbids it with absolute authority. The universe protects its own consistency. But this law has a terrible consequence. Light from distant regions of space takes time to reach us, a long time. The farther away something is, the older the light we receive from it. We see the sun as it was 8 minutes ago, the nearest star as it was 4 years ago, the Andromeda galaxy as it was 2.5 million years in the past, and the cosmic microwave background, the afterglow of the Big Bang itself, shows us the universe as it appeared 380,000 years after creation, when atoms first formed and light could finally travel freely. That is the oldest light we can ever detect. Before that moment, the universe was opaque, a seething plasma too dense for photons to escape. No telescope, no matter how powerful, can pierce that veil. It surrounds us at a distance of 46 billion light-years in every direction, forming a perfect sphere, the surface of last scattering, the edge of observability. And beyond it lies 13.8 billion years of history we can never witness.
regions of space that existed then, but whose light has not had time to reach us, and never will. Because the universe is not static, it is expanding, and not just expanding, accelerating.
In the 1920s, Edwin Hubble discovered that distant galaxies are receding from us. The farther away they are, the faster they move. Space itself is stretching, carrying galaxies apart like dots painted on an inflating balloon. For decades, cosmologists assumed this expansion was slowing down, gradually decelerating under the pull of gravity. But in 1998, two teams of astronomers measuring distant supernovae found something impossible. The expansion was speeding up. Something is pushing the universe apart. We call it dark energy, though that name is a placeholder for ignorance. We do not know what it is. We know only what it does. It acts like a repulsive force, intrinsic to empty space itself. The more space exists, the stronger the push. And as the universe expands, more space comes into existence, which accelerates the expansion further, which creates more space. A runaway process without apparent end. The mathematics are merciless. As dark energy drives galaxies away from us at ever-increasing speeds, their recession velocity eventually exceeds the speed of light, not because they are moving through space faster than light, but because space itself is expanding so rapidly that the distance between us and them grows faster than light can cross it. These galaxies do not vanish instantly. Their light, already en route, continues to reach us for a time, but it becomes redshifted, stretched to longer and longer wavelengths, dimming as the photons lose energy climbing out of the expanding space-time. Eventually, the light fades below detectability, and then true disappearance. The galaxy crosses what cosmologists call the cosmic event horizon, a boundary beyond which no signal of any kind can ever reach us again. This is happening right now. Every second, approximately 3,000 stars slip beyond our cosmic event horizon, lost to us forever. In 1 trillion years, every galaxy beyond our local group, the small cluster of galaxies bound together by mutual gravity, will have receded past this boundary. Future astronomers will look up and see a universe containing only a few dozen galaxies. They will not see the cosmic microwave background. They will not observe the expansion of space. They will have no evidence that the Big Bang ever occurred. The universe will have erased its own history from view. We are living in a privileged moment, an epoch where the universe still reveals its origins, still displays its vastness, but that privilege is temporary. The cosmos is entering an age of eternal isolation, and we are trapped within an island of light that shrinks with every passing heartbeat. But the observable universe has a boundary for reasons deeper than expansion alone. Even if space were not expanding, even in a static cosmos, we would still have a horizon, because the universe has an age, 13.8 billion years. Light traveling at its maximum speed for that entire duration can only cover a finite distance. In a non-expanding universe, that distance would be 13.8 billion light years. But because space has been stretching while the light traveled, those distant regions have moved farther away. The actual distance to the edge of observability, corrected for expansion, is 46 billion light years. This is the particle horizon, the boundary defined by the age of the universe and the finite speed of light. Every point in space has its own particle horizon, a spherical shell centered on that location, beyond which light has not yet had time to arrive. If you could instantly teleport 1,000,000,000 light years away, you would find yourself at the center of a new observable universe, 46 billion light years in every direction. Some of that volume would overlap with what we can see from Earth, but most would not. You would see galaxies we never can, ancient structures whose light has not reached our corner of spacetime. And this suggests something profound. If every location has its own observable sphere, and those spheres overlap only partially, then the universe beyond our horizon is not merely distant, it may be infinite. What is the shape of the universe? Not its local curvature, warped by stars and black holes, but its global geometry, the structure of space-time on the largest possible scales. General relativity permits 3 possibilities. The universe could be closed, curving back on itself like the surface of a sphere. Travel far enough in one direction, and you eventually return to your starting point. In such a universe, space is finite but unbounded, with no edge. The universe could be open, curving away from itself like a saddle. This geometry extends infinitely in all directions. Or the universe could be flat, obeying the familiar rules of Euclidean geometry, where parallel lines never meet and the angles of a triangle sum to exactly 180 degrees. Flat space is also infinite. Determining which geometry describes our universe requires measuring its curvature. Cosmologists do this by studying the cosmic microwave background, looking for patterns in the size and distribution of temperature fluctuations. These patterns depend sensitively on the curvature of space. After decades of increasingly precise measurements from satellites like COBE, WMAP, and Planck, the verdict is clear. The universe is flat, or so close to flat that any curvature is undetectable within our measurement precision, less than 1% deviation from perfect flatness. If the universe is truly flat, it is infinite, not just beyond our horizon, infinite absolutely. Space extends without end in all directions, containing an infinite number of galaxies, an infinite amount of matter and energy. And this infinity has been there from the beginning. The Big Bang did not happen at a point. It happened everywhere, simultaneously, throughout an infinite expanse of space. The early universe was infinitely large and infinitely dense. Expansion did not make it bigger. Expansion made each region less dense, stretching the fabric of space while the total volume remained infinite. This is difficult to visualize. We are accustomed to thinking of the Big Bang as an explosion from a point, a cosmic grenade detonating and flinging matter outward. But that image is wrong. There was no center, no edge. Every point in the infinite universe was compressed to nearly zero separation from every other point, yet the total extent remained infinite. Then expansion began, not an expansion into anything, just the metric of space itself increasing, causing distances between objects to grow. An infinite universe stretching to become a larger infinity, as nonsensical as that sounds. And if space is infinite, populated with infinite matter distributed roughly uniformly, then probability demands something unsettling. There must be repetition.
Consider your body, your brain, every atom in precise configuration. Neurons firing in specific patterns that generate consciousness, memory, identity. This arrangement is complex, but it is finite. finite information encoded in finite matter. In an infinite universe with infinite opportunities for matter to arrange itself, every possible configuration must occur, not just once, infinitely many times. The numbers are staggering, yes. Max Tegmark, a cosmologist at MIT, has calculated that the average distance to the nearest identical copy of you is roughly 10 to the power of 10 to the power of 29 meters, a number so large it defies comprehension. But in an infinite universe, that distance exists and is traversed and surpassed over and over. There is another you out there, beyond the observable horizon, living a life identical to yours up to this moment. Identical memories, identical thoughts, identical choices, and another making slightly different choices, and another in a world where history diverged centuries ago, and another in a universe where the constants of physics differ by infinitesimal amounts. All of this, not speculation, but mathematical inevitability in an infinite cosmos. This is level 1 of Max Tegmark's multiverse classification, the simplest kind. The regions beyond our horizon are not exotic alternate dimensions. They obey the same laws of physics. They contain the same particles, same forces, same fundamental constants. They are simply elsewhere, causally disconnected by distance and expansion, but ontologically identical to our own observable bubble. Your cosmic twins exist, scattered throughout infinity, living lives you might recognize or find utterly foreign, depending on how far away they are and how much their local conditions diverged from yours. The philosophical implications are staggering. If every possible arrangement of matter exists somewhere in the infinite universe, then nothing is unique. Every triumph, every tragedy, every love, every loss has happened before and will happen again infinitely many times. Does this render your life meaningless, or does it affirm that meaning is local, personal, real, regardless of cosmic repetition? But perhaps the universe is not infinite. Perhaps what lies beyond our horizon is not more of the same, but something radically different. In the 1980s, cosmologist Alan Guth proposed a solution to several puzzles about the early universe. Why is the cosmic microwave background so uniform in temperature across the sky? Why is the universe so flat? Why do we not observe magnetic monopoles or other exotic relics predicted by particle physics? Guth's answer: cosmic inflation, a brief period, perhaps lasting only a trillionth of a trillionth of a trillionth of a second, during which the universe expanded exponentially fast, far faster than the speed of light. Space stretched by a factor of at least 10 to the power of 26, smoothing out irregularities, diluting unwanted particles, and driving the curvature toward flatness.
Inflation solved the problems it was designed to address, but it introduced something unexpected. According to the theory, inflation is driven by a scalar field, the inflaton, sitting in a high-energy state. As the field decays to a lower energy state, its potential energy converts into matter and radiation, ending inflation and beginning the hot Big Bang we observe. But quantum mechanics introduces randomness. The inflaton field fluctuates. In some regions, it decays quickly. In others, it continues inflating. And in those regions that continue inflating, space expands so rapidly that even the small regions where inflation has ended become separated by vast, ever-growing gulfs of still inflating space. This is eternal inflation. Once it starts, it never completely stops. New regions constantly decay out of the inflationary state, forming bubble universes like ours, each surrounded by exponentially expanding inflating space that spawns more bubbles. The process is self-sustaining, eternal, and it creates a multiverse of unimaginable scale. Our observable universe is one bubble, a finite region where inflation ended 13.8 billion years ago, allowing matter and energy to condense into galaxies and stars and planets. Beyond our cosmic horizon lies the rest of our bubble, potentially infinite if the decay happened uniformly across an infinite expanse. But beyond that, beyond the full extent of our bubble, however large it may be, lies the eternally inflating background. And within that background, other bubbles, other universes, each with its own causal history, its own galaxies, its own observers wondering what lies beyond their horizon. And here is where things become truly strange. The properties of physics in each bubble may differ. During inflation, certain symmetries can break randomly, determining the masses of particles, the strengths of forces, even the number of spatial dimensions that remain macroscopic. String theory suggests the existence of a vast landscape of possible vacuum states, perhaps 10 to the power of 500 different possibilities, each corresponding to a different set of physical laws. If eternal inflation is correct, every possible set of laws is realized somewhere in the multiverse. Our universe, with its particular electron mass, its specific strength of electromagnetism, its 3 large spatial dimensions, is just one bubble among infinite variations. Most of those bubbles are sterile. Slight changes to fundamental constants render atoms unstable, prevent stars from forming, eliminate chemistry. But in the infinite multiverse, every possibility occurs infinitely many times, including universes like ours, where the constants happen to permit complexity, life, consciousness. We exist in this bubble not because it is special, but because we could not exist anywhere else. Anthropic selection at its most extreme. This is level 2 of Tegmark's multiverse. Beyond the horizon lies not just more of the same, but bubbles with different physics, universes where electromagnetism is stronger and atoms cannot form, universes where gravity is weaker and galaxies never collapse, universes with 4 spatial dimensions where planetary orbits are unstable, an infinite variety, all embedded in the eternally inflating superstructure that spawned them.
But even this may not be the end. Quantum mechanics itself suggests a deeper level of reality, a more fundamental multiverse. Consider the famous double-slit experiment. A photon passes through 2 slits and interferes with itself, creating a pattern that suggests it traveled through both slits simultaneously. But if you measure which slit it passes through, the interference pattern disappears. The act of observation seems to collapse the photon's wave function from a superposition of possibilities into a single outcome. For decades, physicists accepted this collapse as a brute fact. Observation causes wave functions to collapse. End of story. But in the 1950s, physicist Hugh Everett proposed a radical alternative. What if wave functions never collapse? What if every possible outcome of a quantum measurement actually occurs, each in a separate branch of reality? The photon does go through both slits, but in one branch of the multiverse, you measure it going through the left slit. In another branch, you measure it going through the right slit. Both versions of you exist, each unaware of the other, each inhabiting a separate world.
This is the many worlds interpretation of quantum mechanics. Every quantum event that has multiple possible outcomes splits the universe into multiple branches, one for each outcome. The branching is continuous, happening at every point in space where quantum indeterminacy exists, which is everywhere. The multiverse grows exponentially, proliferating into incomprehensible complexity. And because quantum events have been occurring since the Big Bang, the number of branches defies any attempt at comprehension. A tree of worlds so vast that even infinity seems inadequate to contain it. In this framework, what lies beyond our observable horizon includes not just distant regions of our own universe, not just other bubbles with different physics, but entire branches of quantum reality where history unfolded differently. Universes where the asteroid missed the dinosaurs, where your parents never met, where you made different choices, all existing in quantum superposition, separated not by distance, but by the orthogonality of their quantum states. You cannot visit these branches, cannot communicate with them. They are forever sealed behind a barrier not of space or time, but of quantum phase. This is level 3 of Tegmark's multiverse, the quantum multiverse, and it is fundamentally different from the previous levels because it does not require infinite space or eternal inflation. It arises purely from the mathematics of quantum mechanics applied consistently without the ad hoc assumption of wave function collapse. If many worlds is correct, and many physicists believe it is, then reality is unimaginably larger than we can perceive. Every moment branches into countless new worlds, each as real as the one you currently inhabit. And all of it exists in some sense right here, layered on top of itself in quantum superposition. Beyond even this, some physicists have speculated about a fourth level, the ultimate multiverse. Not just all possible states of quantum mechanics, not just all possible physical laws, but all possible mathematical structures. Every consistent set of equations, every logical framework that does not lead to contradiction, corresponds to a universe that exists in some Platonic sense. Our universe, governed by the Standard Model and general relativity, is one such structure. But so is a universe governed by different equations, different symmetries, different dimensionality. Even universes with bizarre properties like closed time-like curves or negative probabilities, as long as the mathematics remains self-consistent.
This is Tegmark's Level 4 multiverse, the mathematical universe hypothesis. The idea that physical existence and mathematical existence are the same thing. If a structure can be described mathematically without contradiction, then it exists, not as an abstraction, but as a real universe inhabited by observers who experience it as concrete and physical. You are not made of matter. You are made of mathematics, a pattern in the solution space of certain equations. And every other pattern that could exist does exist somewhere in the space of all possible mathematics. This level is controversial even among multiverse proponents. It ventures into metaphysics, blurring the line between physics and philosophy. But it raises a profound question. If mathematical existence implies physical existence, then what lies beyond our observable universe is not just space or different bubbles or quantum branches. It is the totality of all logically possible structures, an infinite library of universes, each obeying its own internal logic, many so alien that calling them universes seems inadequate. And yet, for all this speculation, all this mathematics, we must confront a humbling truth. We do not know. We cannot know.
The horizons that surround us are not technological barriers to be overcome with better telescopes or faster spacecraft. They are fundamental limits imposed by the structure of reality itself. At the smallest scales, physics breaks down entirely. The Planck length, approximately 10 to the power of -35 meters, is the scale at which quantum fluctuations in spacetime become so violent that our equations produce nonsense. Distances smaller than this cannot be meaningfully defined. Similarly, the Planck time, 10 to the power of -43 seconds, is the briefest interval that has physical significance. Below these scales, the concepts of space and time may not apply. The smooth fabric of space-time may dissolve into something else. Quantum foam, some call it, a churning sea of virtual particles and fleeting geometries where cause and effect lose their meaning. We have theories that attempt to describe this realm. String theory posits that the fundamental constituents of reality are not point particles, but tiny vibrating loops of energy existing in 10 or 11 dimensions, most of which are curled up so small we cannot detect them. Loop quantum gravity suggests that space-time itself is quantized, built from discrete units like pixels in an image. But these theories are incomplete, untested, perhaps untestable. We have no particle accelerator powerful enough to probe Planck-scale physics directly, no experiment that can confirm or refute these ideas with certainty. And so, at the very foundation of reality, we face a wall, not just an observational horizon, but an epistemological one, a limit to what we can know, imposed not by our tools, but by the structure of the universe itself. Beyond the Planck scale lies territory our current physics cannot map. Perhaps future theories will illuminate it, or perhaps, as some suspect, there is a genuine boundary to knowability, a point beyond which questions cease to have answers, where the universe bottoms out into mathematical bedrock that admits no further explanation.
Some have suggested that the horizons we perceive are not features of reality, but artifacts of simulation. If our universe is a computational process running on substrate we cannot access, then the observable universe might simply be the rendered region, the chunk of data actively being processed. Beyond the horizon, unallocated memory, procedurally generated content that springs into existence only when observers approach, like distant terrain in a video game. This is the simulation hypothesis, popularized by philosopher Nick Bostrom. The argument is statistical. If it is possible for civilizations to create high-fidelity simulations of universes, and if such civilizations choose to run many simulations, then most observers find themselves in simulations rather than base reality. The odds favor simulation over authenticity. And if we are in a simulation, then asking what lies beyond the observable universe is like asking what lies beyond the edge of a game map. The question may be meaningless, or worse, dangerous. Query the wrong memory address, and the program crashes. There are those who take this seriously, who look for glitches in the cosmic code, anomalies in the fine structure constant, unexpected correlations in the distribution of galaxies. So far, nothing definitive, but the hypothesis is difficult to falsify. By design, a sufficiently advanced simulation would be indistinguishable from base reality. The simulators could edit out evidence of their existence, could even edit your memories so you never think to ask. And yet, the hypothesis remains speculative, a modern twist on ancient solipsism.
It does not answer the question of what lies beyond, it only reframes it. If our universe is simulated, what kind of universe hosts the simulation? What are its physics, its scale? And does that universe have its own horizon, its own beyond? The regress is infinite. Turtles all the way down, or all the way up, depending on your perspective. Let us turn to the future, the far future. Trillions of years from now, when the stars have exhausted their fuel and the universe has cooled to a whisper above absolute zero, dark energy will have driven all distant galaxies beyond the cosmic event horizon. The observable universe will contain only the remnants of our local group, collapsed into a single massive black hole. And that black hole, too, will evaporate via Hawking radiation, slowly bleeding mass into space as virtual particles near the event horizon are separated by quantum fluctuations, one escaping while the other falls in. After 10 to the power of 100 years, even supermassive black holes will have evaporated completely. The universe will be a sparse, cold void, photons stretched to wavelengths larger than the observable universe itself. Occasional particles drifting through space so dilute that they might never encounter another particle for eternity. This is heat death, the final equilibrium, a state of maximum entropy where no gradients exist, no structure persists, no computation is possible. In such a universe, the concept of beyond the observable horizon becomes moot. There will be no observers left to have a horizon, no light left to define one, just an infinite, featureless expanse where nothing happens and nothing ever will. The universe will not end. It will simply continue forever in a state of absolute stillness. Unless there are phenomena we do not yet understand, processes that operate on timescales so vast they have not yet manifested. Some physicists speculate about quantum tunneling events that could, given infinite time, nucleate new Big Bangs. Others propose that black hole evaporation might leave behind remnants, stable particles that persist after the hole disappears, accumulating over eons into structures we cannot imagine. Still others suggest that consciousness itself might find ways to survive, encoded in quantum fluctuations of the vacuum, spreading out over cosmic timescales, thinking thoughts so slow that a billion years is a single neuron firing. These are guesses, hopeful speculations against the finality of heat death. But they remind us that our ignorance is profound. We have been observing the universe scientifically for only a few centuries. We have data spanning a few billion years of history. To confidently predict the fate of the cosmos over timescales of 10 to the power of 100 years or more requires extrapolation so extreme it borders on hubris. We do not know what lies in the future, and we do not know what lies beyond our horizon. And perhaps, in the end, these unknowns are the same.
Could we ever send a message beyond the cosmic event horizon? Could we reach out to those distant galaxies already receding faster than light and say, "We are here, we see you, we know you exist"? The answer, according to our current understanding, is no. Light cannot outrun the expansion of space. No signal, no matter how powerful, can bridge a gap that grows faster than causality can propagate. Gravitational waves, which also travel at the speed of light, face the same limitation. Neutrinos, traveling at nearly light speed, offer no advantage.
Some have proposed exotic solutions, wormholes, shortcuts through space-time that could connect distant regions without traversing the intervening space. But wormholes, if they exist, require exotic matter with negative energy density to keep them open. No such matter has ever been observed. And even if we could create a wormhole, we could only connect regions that are causally connected to begin with. You cannot thread a wormhole through a cosmic event horizon any more than you can send light across one. Others have suggested manipulating the vacuum itself. The quantum vacuum is not empty. It seethes with virtual particles, fleeting fluctuations of energy that appear and vanish too quickly to violate conservation laws. Perhaps with enough technological sophistication, we could engineer the vacuum to create signals that propagate faster than light. But every attempt to formalize such ideas runs into the same problem. Faster-than-light communication permits sending signals into your own past. Causality paradoxes. The universe forbids it. And so we are isolated. Not by our technology, not by our biology, but by physics itself. The galaxies beyond our horizon are lost to us, not temporarily, permanently, forever. Any civilizations that exist there will live and die without ever knowing we existed, and we will never know of them. The cosmos has partitioned itself into causally disconnected regions, and no force in the universe can breach those partitions. This is the ultimate loneliness, not the loneliness of being the only intelligent life in the universe. That would be tragic, but comprehensible. This is the loneliness of knowing intelligence might exist, probably does exist, in abundance beyond our reach, and we can never confirm it, never contact it, never share knowledge or art, or even acknowledgement of mutual existence. We are shouting into a void that cannot hear us, and that void is infinite. There is a philosophical tradition extending back to Kant and beyond, that recognizes limits to human knowledge, things in themselves, noumena, the territory beyond the map of our experience. We can never know reality as it truly is, only as it appears to us through the filters of perception and cognition. The horizon of the observable universe is a physical manifestation of this epistemic humility. There are truths about the cosmos, the contents of distant regions, the ultimate fate of matter, the nature of reality at the Planck scale, that we can never access, not due to limitations of our instruments, but due to the structure of the universe itself. Kurt Gödel proved mathematically that any sufficiently complex logical system contains true statements that cannot be proven within that system. Hofstadter and others have drawn analogies between Gödel's incompleteness theorems and the limits of scientific knowledge. Perhaps there are true facts about the universe that cannot be derived from any observations we could ever make. Perhaps what lies beyond the observable universe is one such fact, not because the answer does not exist, but because the question transcends the reach of empirical investigation. Stephen Hawking once speculated that there might be fundamental limits to what physics can explain, that the universe might be comprehensible only up to a point, beyond which lies irreducible mystery. Not ignorance we might overcome with better theories, but genuine inscrutability built into the fabric of reality. Ludwig Wittgenstein famously concluded his Tractatus with the admonition, "Whereof one cannot speak, thereof one must be silent." Perhaps the regions beyond our horizon fall into that category. Whereof we cannot observe, thereof we must remain silent. And yet we do not remain silent. We ask the question anyway. We build cosmological models, extrapolate our physics into realms we can never test, construct multiverse theories that border on metaphysics. Why? Why do we persist in asking questions that may have no answers? Why does the human mind, a product of evolution on a small planet orbiting an average star in an unremarkable galaxy, insist on contemplating the infinite and the unreachable? Perhaps because curiosity is what makes us human, the refusal to accept boundaries, even when those boundaries are carved in the laws of physics. Every civilization that arises, if it survives long enough, must eventually turn its gaze to the horizon and ask, what lies beyond? And even if the answer is nothing, or we cannot know, or the question itself is meaningless, the act of asking honors something essential, something that transcends survival and reproduction and all the evolutionary pressures that forged our minds. The desire to understand, to know, to push against the walls of our cosmic prison and demand answers from an indifferent universe. We are, all of us, made of stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, these elements were forged in the cores of massive stars and scattered across space when those stars exploded as supernovae. You are literally stardust animated by electrochemical processes that somehow give rise to consciousness. And now that consciousness turns back toward its origins, looks out to the cosmos that created it, and asks, what am I? Where did I come from? What lies beyond the edge of everything I can see? The observable universe is not a prison. It is a gift, a brief moment of clarity in an eternity of darkness. We are living in a special time, cosmically speaking, a time when the universe still reveals its history, still displays its grandeur. Future civilizations, if any arise, will inherit a lonelier cosmos, a universe stripped of its deep past, its distant reaches, its evidence of a beginning. They will have to work harder to understand where they come from. We have it easy by comparison. We can see the cosmic microwave background. We can observe galaxies forming in the early universe. We can map the large-scale structure of spacetime and confirm with our own eyes the predictions of our theories.
And what we see is this: we are small, unimaginably, terrifyingly small. One planet among billions, in one galaxy among trillions, confined to a sphere of visibility that encompasses less than a fraction of what might exist. But we are also significant, because we are the universe observing itself. The cosmos has become conscious here in us and turned its attention inward and outward, seeking understanding. That is not nothing. That is everything. One day, the last stars will burn out. The last black holes will evaporate. The universe will slide into its final equilibrium, a cold and silent void where nothing new can ever happen. But that day is far, far in the future. For now, for this brief, shining moment, we exist. We think. We wonder. We build telescopes and particle accelerators and spacecraft. We write equations on blackboards and argue about the interpretation of quantum mechanics and stay up late staring at the night sky, pondering the same questions our ancestors asked 10,000 years ago. What lies beyond the horizon? We do not know. We may never know, but we will continue to ask, because asking is what we do.
It is, perhaps, the most human thing there is, to stand at the edge of the known and peer into the unknown, not with fear, but with curiosity, with hope, with the unshakable conviction that even if we cannot know everything, knowing anything at all is a privilege worth honoring. The universe is vast, beyond comprehension. It may be infinite. It may be one bubble among infinite bubbles in an eternally inflating multiverse. It may be one branch among infinite branches of quantum reality. It may be one mathematical structure among all possible structures. Or it may be something else entirely, something so alien to our categories of thought that we lack even the language to describe it. We do not know, but we are here, now, in this corner of space-time, with these laws of physics, looking out at a cosmos that is beautiful and terrible and mysterious. And that, perhaps, is enough. We are witnesses to the grandeur of existence, temporary, fragile, impossibly improbable witnesses, but witnesses nonetheless. So we continue. We observe, we calculate, we theorize, we build instruments to see farther, think deeper, understand more completely. We know there are limits, horizons we cannot cross, questions we cannot answer, but we also know that those limits do not diminish us. They define the arena in which we strive, the challenge we rise to meet, and every time we push a little farther, learn a little more, expand our understanding by even the smallest increment, we prove that consciousness, fragile and temporary as it may be, is a force to be reckoned with, a flame that burns bright against the darkness. What lies beyond the observable universe? Everything and nothing, infinity and emptiness, other worlds and utter void. The answer depends on which theory is correct, and we do not yet know. Perhaps we never will. But the question endures, and so do we. For now, for as long as we can, looking outward, looking inward, seeking truth in a cosmos that offers beauty but no easy answers, and finding in that very search something resembling meaning, something resembling home. The horizon calls, and we, for all our insignificance, answer back. We are here, we see you, we do not understand, but we are trying, and that, in the end, is what it means to be human, to stand at the edge of everything and refuse to look away.